again, optimized for different situations, right? Whether you are facing a sudden threat versus learning a slow, task versus learning a fast task. You have kind of different optimized systems within your brain. And we know a lot about the mechanisms underlying that. And one could build from that if one wanted to start with.
Yeah, I agree. Essentially, I think there's a number of domains where we know humans are still the benchmark. And I think in this case, why not look at what works, what we know works, especially when we don't know of, sorry. Oh, it's working now. No, it's not working. Especially when we know that humans are still doing better, then that's an avenue to explore, I think.
Thank you for the question. So in this side of the room over here.
Hi, my name is Harrison Ritz from Princeton. I want to follow up on the birds and airplanes idea with a question for David. I wonder if there's like a broader generalization of this idea of redundancy across evolution where different kind of brain regions might serve different capacities but have evolved different kinds of algorithms to achieve those, and whether or not we might miss that with a computational validity kind of approach. And it seems like maybe a commitment there is that animals might differ in their parameters but not in their algorithms, and how we might think that in light of the kind of redundancy that evolution might endow different organisms.
I think the real key, is this on? Are we good? I think the real key is that I'm a firm believer that behavior gets you a large distance, but not all the way. There are many, many, many cases where the same behaviors can be driven by different underlying neural systems. And it is only when you've actually identified those neural mechanisms that you can create probe trials to really separate them. And a lot of times the probes that separate those decision systems are things that really have nothing to do with the behavior. They're kind of extraneous things. So I think in the end, one really has to open up the brain to look at that, which is, of course, illegal in some places. And one has to, therefore, use what techniques one can across that. But I think there's definitely very, very strong evidence that there are multiple decision systems in most species. I'm only really personally comfortable saying, I'll say all mammalian species, but I know my fly colleagues have claimed flies do. I don't think they're matched. I think they're quite different. But there are different systems. And it makes sense because it's really a multiple expert system if you go back to the kind of old AI kind of model.
Yeah. But, I mean, the specific version of that was mixtures of experts across organisms, like at an evolutionary. Like mixtures of experts across, like distributed across organisms within an ecology.
No, mixtures of experts within an organism, right? That what you have is you might train up one network. I mean, Anne gave the great example, right? You might train up one network to do reinforcement learning and another one to do what she calls working memory, which, in fact, train in parallel, right? And are kind of optimized. In fact, one of my favorite things is, given that we've made this discovery that there are multiple decision systems, how do they compete? Who gets to decide who's driving the agent? And the short answer is we don't know, right? That is an open question in science today. People have made suggestions. There's a bunch of theories out there, but nobody, to my knowledge, and this is the field I work in, nobody, to my knowledge, has really definitively figured that out. We know they exist. We can put them into conflict, but the mechanism by which that conflict is resolved is still an open question.
Great. I believe the next fellow in the dark shirt was next.
Thank you very much. My name is Reza Ramazan. I'm from University of Waterloo in Canada. I would like to know the panel's idea on, over the last 10 years, we've seen AI models, particularly neural networks, exponentially going up compared to traditional statistical models. The things that you can do with AI, you cannot really do with traditional statistical models. But there's a drawback to that you lose interpretability here. So you make these complex models and you lose interpretability. And in terms of understanding these models, inference in the traditional sense, we are in the baby stages of those models for now. So my question is that a famous statistician says all models are wrong, but some are useful. So this adage applies here as well. So I am wondering if you think that are we using AI simply because it works and we get good results, though we need a ton of data to train these models? It is not really comparing apples to apples when we compare AI to models that we could understand in terms of inference, in terms of like their interpretation of their performance. But we are making the models very complicated. And do you think that the modern computational neuroscience is going that way simply because it works, or because that is how the brain works? This is a big leap. This is a big step to take, to say that is how the brain works, not that this is how the data is taking us to go that way. And the part that really confuses me is that to make these models work, we need way more data. But on the other hand, human beings, like people, do not need that much data to train themselves to get that. So if you guys could comment on that, I would be thankful. Thank you.
You want to try that one, Chelsea?
I guess I could try. I'm not really someone who is in the neuroscience community quite as much, so I can't comment on all of it. But I guess a few thoughts. I think that like deep learning based models are, in my opinion, far more capable than smaller models. Maybe that's not controversial. I think that what we can learn from them is not necessarily looking at their raw performance, but comparing algorithms. If we have one algorithm that uses something just like reinforcement learning versus one that uses maybe a mixture of reinforcement learning and working memory, looking at the relative performance of those two, I think that can tell us about, like if one has certain capabilities, I think that should be able to tell us useful things without having to interpret the neural network itself. And I guess you can look at like things like emergent behavior that comes out of these systems, like if you put them in a certain environment, what happens and so forth. So I think that, I'm not really a neuroscientist and I don't really work on kind of studying human intelligence, but I think that those, there are still things that are quite useful from that standpoint.
I think it's important to point out that the statistical models can't do a lot of the things that these neural nets can. Whether we can interpret the neural nets is a whole other issue, but the fact is you can't do a linear regression and get this kind of stuff out. And in fact, I mean, going back to the old, the original PDP argument was people tried all that symbolic AI stuff and ray tracing and things like that. It didn't work. No, right? We pushed it as far as it could go, and then the sub-symbolic kind of revolution came along, and in large part because there are things that the brain is doing. Sub-symbolic gives you abilities that symbolic doesn't, and things like settling into data sets and things like that come out. And this is, I haven't been in that world for a little while, but I think one of the reasons that we look at that and we built those sub-symbolic architectures was because it was actually a successful step forward. And I think we are learning, I think that's probably why the brain does it that way. I mean, in some level, the symbolic level gets closer to the working memory kind of stuff that Anne was talking about. It has very limitations. Those limitations are useful in specific places. But in other places, like motor control, that kind of symbolic architecture doesn't really work.
If I could just add one thing in terms of interpretability. So we had more interpretable symbolic models. We've gone to deep Q networks that are much harder to understand why they're working and how they're working. I think a very important domain of computational neuroscience is actually to bridge across levels of modeling description. So I think the kind of models I'm working with are essentially extremely simple algorithmic models But there's a bunch of work that says like, and how could this be implemented, and how can we take those principles that we identify at the high level into something that we put into a more complex structure, and you know, what approximation do we lose by jumping levels, but what can we gain by still taking those high level explanatory principles into more complex structures. So I think there's not that much of this happening, I think, in our communities, but I think it's a very important step in the future to have people working across domains to improve, you know, to get the best of both worlds, essentially.
Thank you for your question. Let's swing back to this side of the room.
Hi, my name is Aditya Prasad, and I'm a master's student at UCSD and the Salk Institute. So in recent years, there have been work using artificial neural networks to model like complex behaviors, for example, virtual rats. And it seemed, correct me if I'm wrong, as though the work that was presented today was with respect to biological agents. I'm wondering if, for example, you can use computational validity to verify the biological plausibility of artificial neural networks. For example, if like self-attention is doing the same computations as in the human brain. And finally, if you can use virtual models to understand the underlying algorithms in the brain. And finally, if embodiment is necessary for understanding how the brain works with respect to behaviors and complex algorithms. Thank you.
So I'll take the first two, and then I'll hand Chelsea at least for the third, since she's been arguing for embodiment directly. I think that thinking about the computational validity, in fact, where we came to in this was in large part because we came from trying to say, are these computational models doing the same thing as the neural systems? And I don't know how many people here are kind of hardcore neuroscientists, but one of the things that us computational neuroscientists would find is people would come in and say, you can't understand the brain this way because you're not looking at every channel in every neuron, and your neuron doesn't have sodium channels that behave this way. And I would always come back and say, is that a necessary component? Where's your abstraction? So the computational validity absolutely, I think, is an appropriate way to think about, is this model explaining the question the brain is performing? And I think that a lot of what the brain is doing is computation. And so fundamentally, we've got to think of it that way. So yeah, absolutely. I think computational validity is the way to think about, is this model actually modeling what the brain is doing? But I'll leave Chelsea for the embodiment question.
Sorry, what was the embodiment question?
Is embodiment necessary?
Oh, is embodiment necessary? I think that it's likely quite important. I think that interaction with any sort of environment allows you to probe your understanding and seek out the parts in which your understanding is wrong and collect more data in those parts. And that's something you can't really do with a static data set without any sort of interaction. And then there's a question of, do you need to interact with the world, or can you interact with the internet or something like that? And I think that the system, the world that it interacts with, is going to be the world that it learns about. You might learn about the internet, which is different than actually interacting with the real world. And so if you want your agent to learn about the world that we live in, then actually having it interact with that world, I think, is probably the most robust way to have it do that.
Thank you.
Thank you.
Hi, my name is Kevin. I am a research scientist at DeepMind. So this question is for Anne, but I also like to hear the opinions of the other panelists. So I really liked your suggestion that humans can see patterns out of pure noise. And correct me if I'm wrong, but you seem to suggest that this is helpful for identifying, for generalization or other purposes. I think this phenomenon also happens in something like hindsight bias, where we saw past events as doomed to happen. So I think it's a really interesting question, but I find it very puzzling that how come that if we have a wrong model of the world, or like a wrong causal model, then how can we generalize well? So yeah, I'd like you to maybe elaborate on that. Thank you.
Yeah, thank you for the question. So I think we are often going to not generalize well. We're sometimes going to overgeneralize and make mistakes. But we are very good at correcting those mistakes and creating, the new appropriate structure. That said, I think, to exemplify the fact that people create too much structure, we on purpose make them learn things that are useless at first. But I think what's happening really is that we do live in a world in which there is a lot of structure, right? All conference rooms look about the same, and there's lots of regularity. So I think in the end, what happens is that we create priors, and the structure we learn relies on those priors. So it's related to the world, and it's going to be for that reason, because there's so much so much existing structure in the world that's the patterns we're going to see and create, and are going to, on average, become more likely to be useful. Does that answer your question?
So it sounds like it's our natural tendency to have a structure.
Yeah, to assume that there is structure.
And then it's helpful in other cases when there is structure existing in the data. Okay, thank you.
Thank you.
Please, yeah.
Thank you for the talks. Greta Tokuda, PhD student at MIT. This is mostly directed to Anne. I'm wondering whether you can comment on the low capacity working memory of humans, and then the link that you are making to AI, specifically transformers. Arguably, transformers are incredibly powerful in many domains, partly because of the multi-headed attention and long attention token spans that they're trained on. So whether you could comment on that link.
Yeah, absolutely. I think, I've heard some of my colleagues say that working memory is the same thing as attention, and I'll disagree with that. But I agree in the sense that attention is also very limited, like very notoriously limited in human behavior, and it's a feature it's shared with working memory, and that's been crucial to the progress through transformers lately. So I do think this feature has been, this aspect of limitation, of limiting, of creating bottlenecks in the information flow essentially has been very successfully integrated in recent deep neural networks. That said, as far as I understand transformers, which I'm not sure I do, I don't think this has been, this limitation has been taken into the active maintenance of information that we see, that is the feature of recurrent neural networks, for example. So in that sense, I don't think that, I think the shared features that have been taken into RNNs are into transformers, but not jointly at this stage. But I agree that transformers seem to be the closest match right now to working memory. Thank you.
Thanks. Thank you for your question. I think we are swinging to this side of the room here.
Thanks. My name is Karim Jerby, professor at University of Montreal, but I just moved to LA for a sabbatical 2 weeks ago. Thank you so much for these brilliant 3 talks. I have a very brief question for Chelsea. I really liked the human in or not in the loop, and then the examples, the samples that improved the performance. And it made me think about whether you've explored looking at learning by observing peers, so looking at other robots doing exactly the same task, just watching, or even social interaction with other robots. And the second part of the question would be looking at the added value of potentially metacognitive processes for the robot to understand why it's doing a task, monitoring its performance, and adding metacognition to the robot. Do you see venues of how that can improve performance?
Yeah, so in terms of observation, we actually have done a fair amount of robots learning from various forms of observation. In a lot of experiments, I guess not necessarily in the ones that I showed, but we have collected data across multiple robots, because then you could just collect a little bit more data that way, and that's one very natural form. Although in that setting, we are using the like knowledge of the robot like encoders, like where the arm is, and when you just observe, you don't have access to that typically. And so, but one setting where you definitely don't have access to that directly is looking at people do things. And we've actually had some experiments where we try to use videos of people doing tasks and actually have the robot use that in various ways. And we've looked at a few different ways of using it, just learning better models of the world possibly, and also using it to kind of direct exploration towards those kinds of things that humans are doing as well. And so, yeah, and one thing that's also really exciting from a robotics standpoint is that there's tons of data of videos of people doing stuff. So we can get really, really diverse data that way. And so it's something that we've explored quite a bit for a variety of different things. We haven't done too much with robots learning with each other. I guess we have done things where we had a paper where we had a robot playing air hockey with a person and would adapt to the person's strategy in different ways, which was fun, and we made it a little bit adversarial and so forth. In terms of your last question of like why the robot might be doing a task, I've done a lot of meta learning, but not metacognition, I think. That's maybe a bit beyond what we've explored.
So I think we have time. Chelsea, if you see your watch. If they're really quick, 2 more questions. If they're lengthy, just 1 more.
Okay. So I'll be trying to be quick. So I'm Chungwan Woo from South Korea. Okay, so my question is, so the title of this session has the intelligent and complex behavior, right? And then I think we need to think about what's really intelligence and what's complex. And then I mean, I remember that in one talk, Sergey Levin talked about the easy universe for us may be a really hard universe for AI and all about the somatomotor systems. And then maybe, that led me think that maybe the simple behaviors for us could be really complex for AI. And I mean, in Professor Reddish's talk, we went back to up to mice, but can we really go back to the single-cell creature, like the single-cell bacteria? They have intelligent, and then they have really seemingly simple behaviors to survive, but it could be really complex for AI. And then, so my question is, when we think about these really low-level biological living organisms' intelligence, seemingly really simple behaviors, and what kind of insight we can get from those kind of line of thought?
Yeah, so what you're referring to, well, one term for that is Moravec's paradox in AI, and I think that this is actually a point that I wanted to bring up, which is that there's a lot of things that we think of as requiring a high degree of intelligence, like winning Jeopardy, or being able to play chess at a very high level. It seems like you have to be very smart to do those things. But we've had AI systems that actually have cracked those problems, and we don't have AI systems that have cracked the kind of toddler level motor control, or even the motor control of a crow or something like that, right? And so I don't think we actually have a good sense for things that might be fairly fundamental to human intelligence. And I think that I think one of the things I like about studying robotics and actually putting robots in the real world is it forces you to, at least from the ground up, like try to solve everything. And I think maybe it forces you to actually find some of the things that are more fundamental to intelligence and to building complex intelligence. But that's somewhat speculative.
So thank all of you. I thank all of you. We'll have to stop there, I'm afraid. I'm sure that many of you have questions, and David and Chelsea and Ann, I'm sure would be happy to engage you. And I just want to thank David and Chelsea and Ann for these really provocative talks. And if I have one question for them, that maybe we could think about for the rest of the days is, in the field of computational cognitive neuroscience, where is emotion? I if I've learned one thing in my 70 years on this planet, it's that most of human behavior is driven by desire, jealousy, greed, love, regret. That was the one emotional word that appeared in these 3 talks, was regret. Chelsea came close. She could have talked about curiosity, a lack of curiosity of a robot to get the drawer handle. Any toddler would have been after those drawer handles immediately, right? But this has just been fantastic, and we look forward to talking more over dinner, all of us, about the themes that have been started here. And thank you guys so much. Dinner. Downstairs? Oh, you're on your own for dinner. Okay. I didn't realize